Okay, welcome back to differential equations. So today we are talking about separable equations. So last time we talked about what differential equations are and what solutions are. So now we're going to study just one kind of differential equation. Okay, so the first kind of differential equation that we study are also the easiest, and they're called separable differential equations, or just separable equations. And these are the ones that you wish are on every exam, but they're rarely going to be on exams. Okay, so what are they? These are differential equations, which you have to do a little trick. If we write the derivative as dy dx instead of y prime, so that's the first step. And then I'm going to put this in quotes, view dy and dx as variables that we can algebraically move around and manipulate. Then if you do that, then we can write the differential equation in this other form. So we could write it as a function of x dx equals a function of y dy. But what this is really saying, well, it's in the name. It's saying that we can separate algebraically the variables. So you can't just make up your own rules, you have to use algebraic rules. You can algebraically separate x from y. So all the x's are on one side, all the y's on the other, including the dx on the x side and the dy on the y side. So writing this is just saying, yeah, I got all the x's on the left, and then this is saying, oh, I got all the y's on the right. And I'm just calling them functions because they only have those variables in them. Now, the reason I say view is because technically speaking, to pretend that dy and dx are their own variables actually requires like very sophisticated justification that we're not going to get to in this class, so we're just going to pretend like, okay, we just know dy and dx can be treated as variables, and that's it. We're just going to do it. My hair is getting too long. It's in my face now. Okay. All right. So that's the idea. Now, of course, examples make it much more clear and obvious what we're doing. So let's just jump into that. Okay, so here's a differential equation. It relates x and y and y prime, so it's a differential equation. And I claim that it is separable. And to show that, the first step, of course, is to write y prime as dy dx, and then we can pretend dx is its own variable, and then we can multiply it across because we're treating it as a variable that we can do algebra to. So I can multiply it to the other side, and then I now have my x's on one side and my y's on the other. So in the previous format, this would be like f of x, and this would be g of y. Whoops, g of y. So it doesn't actually matter which side you move the y's and x's to. So up here, I had the x's on the left, but that's okay. You can flip them around if you want. Okay, so then, why are these the easiest differential equations? Because to solve this differential equation, all we have to do is, once we show we can separate it, so once we have this, we just have to integrate both sides. So to find a solution now, to the differential equation that we started with, we just need to integrate. So in this class, not only do we have to remember derivatives, we also have to remember integrals. So we are going to integrate both sides. And we have to remember our integration techniques. So, one second, I gotta fix this. My hair's in my way, I can't focus. Okay, my lockdown hair has been locked down for now. All right. Okay, so integrals. Remember for integrals, oh God, my hair's in my way again. Okay, whatever, power through. I have to add 1 to the exponent and then divide by it. I'll leave some space there, so this becomes x squared over 2. This becomes 2x. So what am I missing? Well, you might remember from calculus that if I don't have limits of integration, I don't have the fancy numbers on the ends of the integral, then I have to add a constant. So we're going to do that. So then this is it. This is a solution. So this would be an implicit solution because I don't have y solved for. But we're not actually done because we're going to make it much better. So notice that I have these 2 constants. So what is that saying? That's saying that I don't just have a solution. I actually have many solutions. I should have said I have an implicit solution for any choice of C and D. So for example, C equals 1, D equals 10 gives me this solution. So that's one solution. And that hints at something that we're going to do a lot here, which is it's actually very unnecessary to write 2 different constants. I can just think of them as one constant, and we can see exactly why. Why would I not just combine this 1 and this 10? So I could rewrite this in several different ways, but one way is to just subtract the 1 over. So whenever I have 2 constants, I really just have 1. I can think about it as I subtract it over back up here. And then it really doesn't matter that this is a difference of 2 constants. It's really just a constant. So that's what we see going on here. Why would I write this as 10 minus 1? I could just write it as 9. And so you're just saying that there is a constant there. Doesn't matter what you call it. So what we often do in this class is we rename constants to make things look nicer. So we just rename this to be C. And then we say that this is the solution. This solution is a lot better looking. So this is a very common trick. So we just rename this to be C. When you have multiple constants added together, then just combine them into one and call it C. Or whatever letter you want, that's fine too. Because the point is that it still is a whole bunch of solutions. So when I say that this is a solution, I'm really saying like I have a whole bunch of solutions, one for each C and D, and I still have the same solutions here, but I'm just saying that I just have to pick the end constant. I don't have to pick 2 constants and then subtract them. It's the same result. Okay, so why is this okay? Let me write that down in writing. Why is this changing names of constants okay? Well, it's really because any choice of D minus C is a solution. So you're getting all these solutions from different choices. But each one corresponds to a choice of just C in the second way of writing it, in this way of writing it. So you're still getting all the same solutions. You're getting a different solution for each choice, each number that you put there. Okay, so both y cubed over 3 plus c equals x squared over 2 plus 2x plus d minus c. And the other one, the nicer looking one, the more reduced one, they're saying the same thing. They're saying the same set of solutions, which we call, sorry, they're saying the same one parameter. So this is the fancy word we're learning right now. One parameter family of solutions. So what that means is, where does the one come from? The one comes from the fact that any choice of one constant gives you a new solution. So these are my two one constants that as I range through different numbers, I get different solutions. And so it's my parameter is that constant that's changing. So meaning a set of solutions, not just one, depending on one arbitrary constant. So that's where that one is coming from. If it was dependent on two arbitrary constants, which we will see happen, then it would be a two parameter family. And you might think like, well, this is two constants. Well, not really. It's one constant written in a funny way. It's like saying that 10 is two constants because I can write it as 9 minus 1. No, it's just one constant. Okay. And then, so like, what are the then you might say something like this, just to use the language more. So then you might say like y cubed over 3 equals x squared over 2 plus 2x plus 7 is a member of the family because it's one choice of C. And then you might say that this is another member of the family, it's included. And so there are infinitely many. But we're not, when I say solve a differential equation, I'm not saying write down all infinitely many. I'm saying write down the one parameter family. So this is what I'm saying is the solution that we're looking for. Okay, so one thing to notice is that just by virtue of using integrals, this will always happen when we solve a separable differential equation. So we'll keep seeing this. So solving a separable equation always introduces some sort of plus C. So solutions that we get this way will always be one parameter family solutions. Okay, so let's just get down to practicing a few more so that we can practice using this language to do stuff that you already sort of know how to do, because really we're just doing integrals, which you've seen before if you're watching this video. Okay, so let's solve. So again, when I say solve, I mean find the one parameter family of solutions by using this technique. That's what that really means. When I just write the word solve, I mean all that. Okay, so first we're going to separate because I'm only giving you separable ones. So all I have to do is multiply that denominator over, write the y prime as dy dx, and then I can view my dx on the denominator as a variable, so then I can multiply it over. And then just have to integrate both sides, and I have to remember my integral rules. And I'm now a matured differential equation solver, separable differential equation solver. So I can skip ahead and just notice that the constant that would be on both sides, I'm just going to combine them anyway and rename them. So I'll just jump over and only add it on one side. So then this is, just to use all the fancy language we know, it's an implicit, because it's not a function of y, an implicit one parameter, because it's got that one constant, which gives you a bunch of solutions as you change the constant, family of solutions. Okay, so the actual example is very quick, right? That's all we got to do. Okay, so you can already picture maybe how it could get difficult. And it could get difficult if you don't know how to do the integral. So keep that in mind, as I only give you ones you can actually do. There are ones that you can't do. Okay, so here's another one. Here, dx and dy have already been separated, and so the next step is very easy. I just have to add the y dy to the other side, and then I can integrate, and I have to remember the integral of e to the x is e to the x, and the integral of y is y squared over 2, and then I add a constant. So again, this is another one parameter implicit solution. You can say it in different ways. Okay, a couple more examples just to remind you of these various integrals. So this one, y prime has already been written as dy dx. Now I got to get my variable separate. So if I divide by the y, I'm going to write it like that, and I'm going to multiply the dx over like that. Now when I integrate, I have to remember yet another integral, the integral of 1 over y dy, that's ln of y. Got to remember that. So this is the one parameter family. It's implicit, but I can actually change this one to explicit if I remember how to get rid of that log. I have to use exponentials. So if I think of it, I can think of it in many different ways, but I can think of it as e-ing both sides. Then on the left, I now have y, so now I'll have a nice function instead of a relation, so I'll have an explicit solution. And then over here, I'm going to play a little trick. So if I add exponents, that means I get to multiply by the base to that exponent. And now to make things look nicer, I'm going to use this trick again. E to a constant is just another constant. So I'm going to rename it to just be C again. And then it looks much nicer. So I'm just going to rename this and call it C and then stick it in the front. If it's being multiplied, I can move it to the front. So that's my solution. So now it's explicit. One parameter family. Because it's a function, y is a function of x. Okay. And of course, right now, you're just trusting me that these are solutions, that this actually worked. But what you could do is you could take derivatives and plug them back in to make sure they actually solve the differential equations that we started with. So do that if you like, or you can trust me. Okay, let's do one more that will also reveal another trick. another renaming trick that can come in handy. Okay, separate. So I'm going to multiply the y, multiply the dx, and then I'm going to integrate. So I always like to add the plus c to the right side, but you could always add it to the left if you want instead. That's fine. Okay, so this solution is always nice if you can like identify your solution, like what kind of thing is this? And it's actually something you know, but it's hard to tell unless you play this renaming constants trick. So let's do that. So here, you can make the solution look a bit more familiar. By renaming the constants. So first, let's multiply by 2 on both sides. Oops. So then that c becomes a 2c, but I'm just going to rename it to c because I don't care that it's 2 times a constant. It's like saying 10 is 2 times 5. It's the same thing. But then that's usually what we're used to doing. It still doesn't look that familiar. But if I add my x squared over, maybe it looks a little bit more familiar. But then I'm going to do a renaming trick where that's less obvious. I'm going to rename c to be c squared. And now you might be able to recognize that this is a circle. Well, it's a circle for each choice of c. So this is another implicit one parameter family of solutions, but this one we can actually visualize the solutions are just circles. So any circle that you pick, whatever circle you pick, is another solution to this differential equation. Okay, we haven't talked much about graphing solutions and trying to understand them visually, but we'll get to that someday. Okay, so let's see. I think that's basically it. So separable hopefully is not too bad. Just some things to note though. So just because you can separate doesn't mean you can solve. So why not? Well, what if the integral is super hard to do? Then you're sort of stuck. So if you can't do the integral, then you're stuck. To think about that later. And then a sort of deeper question that we'll think about later is how do we know if the thing that we're getting, so we always get this one parameter family of solutions, how do we know if what we got is actually the only solution or contains all the solutions? So for example, going back up here for a second, if I give you this differential equation and you do this process, then you'll end up with this solution. But how do we know that those are the only solutions? What if there's other solutions that arise by doing some other method? So we don't know yet, so be aware of that question. It's a very important question. Sort of like saying, in algebra, you solve things like this. You use the quadratic formula. And then how do you know that that quadratic formula gets you the only solutions that work? Are there extra ones out there that you didn't get somehow? Okay, so that's an important thing to think about. But for now, you should just practice doing separable equations and solving for the one parameter family that pops out. Okay, so that's it for this one. See you next time.